First of all, I must thank the organizers for inviting me to this interesting meeting, particularly Satyabrat and Brijesh. Also, thanks to the community to make me feel like I'm a part of the community. So I could meet so many good friends. So the interesting part of this session, I was noticing that there are already 3 different topics. None of them have any relation to each other. So I am going to give a 4th very different topic that has no relation to the previous 3 topics. Of late, I have been trying to understand how the electron passes through a Skyrmion field, and based on that understanding over the last 2 years, this talk is prepared. The work is mostly done by my postdoc, Hall01 Swai, and my PhD student, Arijit Mandal, and my long-term collaborator, Professor Shashi Satpathy. There are few slides for the so there are few slides for the students how to mathematically define a Skyrmion. So if you have already seen this kind of picture, that means that the spins at a particular site in a magnetic system is not necessarily parallel or anti-parallel to a next neighboring spin. It can have a canting arrangement, and if the canting arrangement has certain topology, it's a kind of a topological non-collinear spin structure, and Skyrmion is one of that kind. To understand it, what you can think of is that you have a magnetic field, which is a continuous vector field at any point has direction in any way, can be defined by the polar angle theta and phi. Just project that continuous vector field on a 2-dimensional space. That will give you the 2-dimensional topological spin texture. Mathematically, you can take care of the theta and phi using few parameters, where lambda here as the radius of the Skyrmion or the topological spin texture, m is the winding number, gamma is the helicity, and phi is the one which wraps around the disk as alpha goes from 0 to 2 pi. So at the end of the day, what we are representing is a 3-dimensional continuous vector mapping into a 2-dimensional field. Now I'll give you some examples. If you take gamma is equal to 0 or pi, you have a nil type of spin texture. If you take gamma is equal to pi by 2 or minus pi by 2, you have a block type of spin texture. Similarly, you can play with the winding number m. You can make it plus 1 or minus 1. You can create Skyrmion and anti-Skyrmions. These are few of the figures you must have seen on the internet, that this kind of non-collinear spins you can arrange like Skyrmion, bimeron, skyrminium, and bimeronium, but just by playing with those parameters. In the experimental domain, so there are sufficient advancement, where people are able to control the design of such non-collinear spin texture. However, there are issues whether they live for a long time, whether they can be stabilized, whether the Skyrmion itself is moving. I am ignoring all of them. I am assuming that the experimental community are progressing fast enough to assume that the Skyrmion can be settled, rigid, and can be made stationary. Now, if the Skyrmion can be settled, rigid, and stationary, then if I allow the electron to pass through it, what kind of transport we can generate and what kind of fundamental quantum physics we can create. That's where my work comes. Mostly the talk is summarized on 3 components. First of all, I will consider a Skyrmion crystal, where the Skyrmions are arranged periodically, and then try to see the itinerant electron passing through this crystal and what the transport is. The second component is that, as we know, that it's not always possible to create a crystal. There can be local Skyrmion clusters. If you have local Skyrmion clusters, thus they produce a local potential, and when my electron pass through that local potential, what kind of scattering will happen. And most of the time in theory, we look at the asymptotic limit, but here we look at it in the real dynamics component at each point what is happening with time. And finally, of course, we'll see at the end of the day, at the asymptotic limit, what are the points that we are preserving. This is the work just last few days back, we just put it on archive. So I don't know whether I can do justice to all the chapters, but I request to get the details, please go through these 3 articles. So we'll start with the crystals, the skyrmion crystals. For that, we built a model Hamiltonian. The model Hamiltonian is such that, assuming that the skyrmion is rigid, these are my free electrons or the itinerant electrons are available. They can have some random spin when they enter the system, but they will start hopping with each other. And that hopping we represent with a tight binding component. And this itinerant electron, its spin will couple with the rigid spin provided by the skyrmion through this Hund's coupling JH. The problem is that if we look in the global spin basis, the itinerant electron that you pass through are either up or down. However, in local periphery, the spins of the skyrmions are varying. So to bring that to the local spin basis, we'll try to make some transformation. This transformation matrix are written this way, so that the local electron, its component on the skyrmion spin site and opposite to it also are addressed. Calculate the Berry curvature in the standard way, and if you can calculate the Berry curvature in the standard way, it gives us a topological Hall conductivity. So what we found, which is amazing, not only by us in the past, Nagaos and others have done in the past, that this, when we plot this topological Hall conductivity, we notice some discretization of it. Okay, what is that now?
This for recording.
So that was not recording?
This recording, but this off हो गया.
So first part of my talk is not recorded? I'll reduce my registration fee now, reimbursement. Okay, so what I'm trying to see is that the topological Hall conductivity now shows certain signature of discretization. This discretization, in a sense, one can think of a quantization. Now that quantization brings some aspect to our understanding, because if you take a homogeneous electron gas, you subject that to a uniform magnetic field. All of us know that it quantizes and produces the Landau levels. So that excited us to explore further that if we are able to discretize using an emergent magnetic field of a skyrmion, can we play around the magnetic field? Can you tune the magnetic field and see that if you can tune the discretization of the topological Hall conductivity? Now, to tune the magnetic field, you need another external field. What better works other than the Raspa field? You can apply a field normal to the skyrmion plane, and that can serve as a Raspa field, and which I introduced by tweaking my Hamiltonian to some extent. Adding a Raspa component to my already model Hamiltonian, that is the Raspa component. And this Raspa component brings out an emerging magnetic field also, in addition to the magnetic field that the skyrmion has given. Now I have a new magnetic field, and both for skyrmion and anti-skyrmion, I do see that new magnetic field. And depending on the strength of the Raspa coefficient, which I have defined through some alpha r, I am trying to tune the magnetic field. Here is some a cartoon. As I play with the Raspa electric field, I can see that my hopping interactions is now altered. Now bands at some point are becoming very flat, nearly flat in fact, and then again they are reversing back to a dispersion band structure. When they are reaching to a nearly flat band, then what happens to the topological Hall conductivity, that we'll try to see. Okay? So I have two pictures. One's the red one where there was no Raspa field, or we didn't apply any Raspa field, and the blue one where we applied a strong Raspa field, 0.5. You can see that the blue one is much more flatter compared to the red one. And when the blue one is much more flatter, you can see the plateaus are much stronger. In fact, what it suggests that we are able to emulate the two-dimensional electron gas in a uniform magnetic field through this Skyrmion picture by applying a Raspa electric field. So the underlying mechanism is as follows. The red one here represents the Skyrmion magnetic field distribution in the system, in the real space. The blue one represents the magnetic field generated by the Raspa. They try to compensate each other. When they try to compensate each other, we have a net finite uniform magnetic field. That gives us this nice plateau-like stuff. To compare it with the real homogeneous electron gas in a uniform magnetic field, we just presented the result for a square lattice. In the square lattice with uniform magnetic field, that are the red ones, and the one that we generated by manipulating our Skyrmion magnetic field are the blue one. They have beautiful matching. Now, did I get enough information from it? Probably there are more fundamental information than I thought, right? We saw that for each band, when we looked at the chain number, that by integrating the Berry curvature, the chain number also for each band is different. And then we noticed that as the strength of the Raspa field changes, the topological character of each of the band changes. So what happens, for example, I have just shown the lowest two bands for which the chain numbers are defined. For the lower one, the red one, the lower band, and the blue one, the upper band. Right? The red one shows in the beginning, it has a 0, right? It has a -1 chain number, and the blue one has a 0, even -2 chain number. Okay. Now what happens as I apply the Raspa field stronger, these bands start touching each other. Once they touch each other and they open up a new gap, the moment they open a new gap, the chain number changes. You can see that on the blue bands, the chain number moves from C2 is equal to -1 to C2 is equal to -2 as the Raspa field strength changes. Similarly, the chain number of the red band moves from -1 to 0 as the Raspa field changes. Not only that, since the title of the session was about the edge state, I tried to explore some edge state that might have been there in the system. So for that purpose, I didn't take the crystal. I took a ribbon of it. When I took a ribbon of it, basically I confined in one direction while allowing it to be infinite in other direction. I could notice some edge bands. The blue and red thick lines represent the edge bands. Their characters can be noticed by seeing the huge probability density at the edge of the ribbons. Okay. These edge bands are interestingly have different slopes or different group velocity. And in fact, this is a simulation done with lesser number of sites. Later, when we checked that we take a large ribbon, we can clearly distinguish the edge bands. Nevertheless, the important factor is that when the group velocity change, you can alter the direction of the charge propagation on both the edges. So it allows us to define or tune the charge direction propagation, right? For alpha r is equal to 0.25 as a critical point, there is no net charge propagation on either of the edge. But for alpha is equal to 0 or alpha r is equal to -0.75, just as means that some changes in the color, I could have a net charge propagation. In a sense, I am creating a net edge current in the system. So having said that, there are more into it that we could see that even the topological Hall conductivity has a sign reversal. It can become negative to positive. Not only for the Skyrmion or nil type, actually we noticed that all sort of systems have similar sign reversal depending on the type of the non-collinear spin texture and the strength of the alpha r. But there are certain universality to it which shows that sign reversibility of topological Hall conductivity in Skyrmion. Okay. Now, I don't want to present the result for all possible spin texture, but we found that we can connect all kind of Skyrmion types and all kind of applied field, be it Raspa, Dresselhaus or Weil, and all of them will be mapped with each other in some way, and whatever results I have presented so far have the universal phenomena. Having said that, now we'll move to the second part of the talk. In the second part, we will not look at the crystal. As I told you, we will look at a single skyrmion, isolated skyrmion. It can be a bunch of skyrmion as well. We want to see how the electron propagates and dynamically what happens at each particular point of the space. Now, to that, we have to relook at the potential created by that particular skyrmion. This potential has 4 components. You can 5. You took away 3 minutes. So you are my friend. So yeah, I'll be done. Don't worry. So there are 4 components to the potential. Basically, depending on the electron you are sending, you are sending an up electron or a down electron. These 4 components makes our life complicated. Now, my electron when moved through the skyrmion, it sees all these components of the potential. Naturally, we try to solve a second order, the Schrodinger equation, time-dependent Schrodinger equation. And it looked easy to us in the beginning because many people have done this time-dependent Schrodinger equation. In fact, for the students, there is a beautiful article in American Journal of Physics in 1984. It has taught us that you take a regular non-spin dependent scalar potential and see how the electron passes through this scalar potential and what the dynamics of it. However, our life becomes complicated because the potential has a spin dependent component and there are 4 components infused into one. So for that we developed a method which I name as hybridized technique for operator splitting with forward elimination and back substitution. The algorithm is presented here. I will not go to the detail due to the lack of time. But let's understand that first look at a one-dimensional non-collinear spin texture. I just took a slice of my 2-dimensional skyrmion and just one-dimensional. I pass through a spin-off electron, that is a Gaussian wave of the spin-off electron. It saw the potential generated by the skyrmion, and then it got scattered. Some of them passed through, some of them back scattered, and importantly, even if I send a spin-up electron, the spin-up electron generated a spin-down electron, which I call spin flipping. And that is where the interesting part lies. You send a spin-up electron, you are able to split it, filter it, and create 2 spin-up and spin-down currents. Okay? Now, in my whole problem, if I look at a parameter that tells me the story, that the parameter is a 2j over ke. The K is the kinetic energy of the electrons I am sending, and J is the strong Hund's coupling. Now I can say that if beta is less than 1, means my kinetic energy is much larger. If beta is greater than 1, my kinetic energy is smaller. Now if my kinetic is smaller, my electron is expected to scatter back more than transmitted back. And if kinetic is larger, we expect electron to move forward larger. So we took 3 regimes. One is the high kinetic energy. And in the high kinetic energy, as expected, large chunk of the spin-up electron moved further. Or if you have sent a spin-down electron, a large chunk of the spin-down electron moved forward. But irrespective of the strength of the kinetic energy, you always see a spin flipping. You always see a finite spin, opposite spin current. And you always see a secondary spin-flipped scattered wave. So electrons iteratively flip their spin and significantly influence the outcome. Then we reduce the kinetic energy. As I reduce the kinetic energy, I saw a large chunk lying inside the skyrmion potential. It is almost lying for longer time, but eventually after a period that also vanishes. However, I further lowered the kinetic energy. This stayed for a longer period, which we have defined as a long-lived quasi-bound localized state. I was excited. I thought that we have now found a new way of creating a qubit. My excitement vanished because after long time that still disappeared. Nevertheless, it's a new understanding to our opinion that we can create localized quasi-bound state. Okay, now I explain the every results in a one-dimensional non-collinear spin texture. I can take you to the real 2-dimensional picture. The story is no different. This is how the Gaussian beam, the electron beam passing through, it hits the skyrmion potential at the center. As hits, it creates a spin down electron as well, spin flipping. Now the story is here for both high energy and low energy spectrum. As I told you, the story is no different, just that the visualization of the two-dimensional, the propagation of the electron in the two-dimensional non-collinear spin texture you'll see here. For either when you pass the spin down electron or when you pass the spin up electron. The story is that it creates a lot of backscattered state. We reveal a distinct secondary wave font associated with a back converted spin component. To our knowledge, that has not been seen in the literature so far. More than that, when we looked at the scattering cross-section, the scattering cross-section lost the symmetry as we increase the beta, means as we decrease the kinetic energy. And the loss in the symmetry indeed creates a transverse charge and spin current in the system, which nowadays everybody is looking for quantum technology. Now, if I have 2 minutes, I'll just zoom through the 1 minute, okay. If I have 1 minute, I'll just try to tell you that what we are now exploring. We are exploring what happens at the asymptotic limit. Local phenomena we understood. At the asymptotic limit, the details are in this paper. We develop a Green's function formalism. There was no other way around it. Basically, we try to see the electron pass through this skyrmion, and we looked at the far away regime. We calculate the scattering cross section, we calculate the current. There are few interesting pictures we noticed. One is that in the conductivity, you see a dip here and a divergence here when your kinetic energy is close to the Hund's coupling. This picture you might have seen when your electron scattered from a noble gas, the low kinetic energy electron scattered through a noble gas. Either they see a high transmission or a minimal transmission. And that was given to us by Ramsauer and Townsend. So what we found that this skyrmion can create a Ramsauer-Townsend dip with low kinetic energy. Not only that, actually as we increase the winding number, we can see n number of local resonances depending on the strength of the winding number. Now, when we examined further, we found that actually the emergent magnetic field is changing with the winding number, and the average magnetic field one can calculate as m is proportional to m, and then when you map it with the Landau level, your Landau level energy is n plus h bar omega v. So we are able to create these Landau levels in this skyrmion in the system, and also you can have a situation when there is only a spin current. By tuning the kinetic energy, you can, of course, you have topological spin and charge current. You can completely filter those charge current and you can have a spin current. With that, there are many take-home messages. Now, since the chair is up and staring at me, please read through these points. Okay, thank you very much for your attention. Yeah, please.
Okay, when you actually pass a spin-up electron packet through this skyrmion potential, so you are showing that there is a spin flip. So why it will not only spin flip, it is in the x or it is in the x direction? What prevents?
I didn't get it.
So basically, spin up or spin down, right?
Mm-hmm.
So there are in the x direction or y direction, it can change its orientation as well, right?
Yeah. So okay, maybe I'll go to the potential, then I'll get your question well. So okay, first just look in any cross section of the potential, right? There are 4 components of the spin you can define. If you have a spin up electron passing through, it is a magenta color. The spin down has a the yellow color, and the flip potential has this green color. The flip potential will try to flip the spin inside the system, right? In whichever way you pass, it will flip the spin. Once it flips the spin, it now, suppose the spin up electron has flipped the spin to spin down. Now that spin down electron will see a barrier. Right. Now I am saying in one direction. Now you can imagine in two-dimension picture, you have a really a right vertical, a two-dimensional barrier or two-dimensional spin. So it can flip and pass through in any direction. But yeah.
So,
There are a lot of questions.
okay. Maybe we discuss.
Maybe we can.
Yeah, we can discuss. Yeah.
Yeah, Ranjit, so in your first work,
Mhm.
you get the topological phase.
Uh-huh.
In your Skirmian lattice, so each Skirmian has a single winding or you need higher order Skirmian to get the topological phase?
You get a topological phase for all winding. So, but the
So n is 1 or n is 2, 3, 4? If I increase the winding of each Skirmian, so do I get
in the first part, right? Okay. So I think with winding you change the topological. By fixing the topological, by changing the magnetic field also you change the topological number.
Yes, yes.
Yeah.
Right. So in your case, it's fixed, right?
Yeah, yeah.
And the second question is the edge state.
Hmm.
So you are getting the edge state along like one parallel edges.
Hmm.
Is it because of the propagation of the Skirmian in xy plane?
Skirmian is not propagating, it's the electrons.
Propagation, spin orientation of the Skirmian.
No, it is due to the asymmetry in the group velocity at a given k point. Let me go back to that point. So if you look at this, this is one particular band I have defined to be red band. Another is blue band. The K1 is the group velocity at this particular point, and these two have same. But at particular K, the green band has different slope or higher group velocity compared to the red band.
But
So
I
when
want to see in the real space, in the L dot.
this one,
No, no, no. D. You see the edge modes are along two edges.
edge modes are along two edges. Yeah.
Yeah, so why not in the total?
Because I took a ribbon other direction, I have made them infinite, right? It is not a cluster.
No, no, if you look at the
No, but Tanmay, रुक एक minute यार. हाँ.
if you do the real 2D, the XS2D system, right? So if you do the local density of state
हाँ.
of the 2D, the edge modes are all over the edges or you are getting it with
All over the edges.
all over, yeah, okay.
Yeah.
No, that I agree.
Yeah.
But your answer is also yes.
Okay, I think Amit had a question.
So all of these calculations were in real space, right?
Well, I did the scattering in the real space, the band structure in the momentum space. The crystal, I took the momentum space.
So one speculative idea is that let's say I construct a lattice of these carnions and identical lattices so that I can work in the momentum space of the supercell of Skirmion space. Then I can generalize all of these concepts in the metallic transport
You are right, yeah.
which will give me some sort of your universal relation should show up very analytically cleanly there.
Yeah. But there will be more band folding when you take a supercell and create a periodicity of that supercell. एक संभाला नहीं जाता, you want, okay.
But in momentum space it's easy to
Yeah. Okay. Thank you,
Okay.
Chair, for accepting me, tolerating me.